Hello my dear children of class 12 science. Today again I welcome all of you through this mode of teaching that we are already following called YouTube mode. And today's class we again do continue. Again we do continue with the chapter that is semiconductor electronics. Okay. Now this is the first chapter under unit number 9 and we are about to complete the chapter, and today we will complete this chapter also. Okay. Now till last class, we have done up to the types of semiconductor, especially with intrinsic semiconductor. We learn in detail about intrinsic semiconductor, also called pure semiconductor. Then even we classify another semiconductor called extrinsic or impure semiconductor. Now you know that extrinsic or impure semiconductor are basically classified into how many types? Two types. One is called N-type semiconductor and next is P-type semiconductor. Now this classification of extrinsic or impure semiconductor is on the basis of the addition of impurity atom to the pure semiconductor. And you know that when we make extrinsic semiconductor, we can add either trivalent atom, impurity atom, or pentavalent impurity atom, okay, to the pure semiconductor. The trivalent means like valency 3 and pentavalent means valency 5. But depending upon this trivalent or pentavalent impurity atom that we add in pure semiconductor, okay, the semiconductor like extrinsic semiconductor can be made as N-type semiconductor and P-type semiconductor. Now the name suggests as N-type means N indicate the negative charge. And you know negative charge are the nothing but electrons. Okay, so why it is called N-type semiconductor and what is the advantage of this, so that you learn in details. So let me start today's class with N-type semiconductor. Now N-type semiconductor is an extrinsic semiconductor obtained by adding what? Pentavalent impurity atoms to a pure or intrinsic semiconductor. Now pentavalent means like valency 5 elements, okay, and they lie in group 5 of the periodic table. Now if you look at the pentavalent impurity atoms like phosphorus, okay, antimony, arsenic, these are all the example of what? Pentavalent impurity atoms, okay, and they have valency 5 or valence electron 5. So when we add this pentavalent impurity atom to the pure semiconductor, then we can always see that this 5 valence electron of this pentavalent impurity atom always share with, okay, with the with your what? Pure valency or valence electron of what? Your pure semiconductor. But out of 5 valence electron, 4 of the valence electron of pentavalent impurity atom will share with the pure semiconductor, valence electron of pure semiconductor. Okay, so that by adding number of pentavalent impurity atom, the number of free electrons increases, so that the conductivity increases. Now in order to understand in more detail about this N-type semiconductor, just let me show you this diagram. So these are all trivalent, or they are all what? Pure semiconductor. These are all intrinsic or pure semiconductor. Okay. Now like silicon, these are the what? Conductor, semiconductor made up of silicon or germanium atoms. Okay, valency 4. So every pure semiconductor, intrinsic semiconductor has 4 valence electron in the outermost orbit, like 1, 2, 3, 4, 1, 2, 3, 4, like 1, 2, 3, 4, 1, 2, 3, 4, like that. But if you add one of the impurity atom, if you add pentavalent impurity atom having valency 5, that means the outermost electron has 1 valence electron more than the silicon or germanium atom, then what happened? Out of 5 valence electron present in the pentavalent impurity atom, okay, 4 of the valence electron will share with the neighboring silicon or germanium atom. Like you can see, this is pentavalent impurity atom whose 1 valence electron will share with the valence electron of this silicon or germanium atom. Similarly, 1 valence electron of pentavalent will share with 1 valence electron of silicon atom. Similarly, another valence electron of pentavalent impurity atom also share with another valence electron of silicon atom or germanium atom. Similarly, this valence electron of pentavalent, this pentavalent, plus 5 is pentavalent impurity atom, share with one of the valence electron of this neighboring silicon atom or germanium atom. So out of 5, 4 has been shared. So when they share the electrons with the neighboring silicon or germanium atom, then they form what bond? Covalent bond. See, these are all what bond? Covalent bond. So that means every one pentavalent impurity atom has one excess of electrons. That means this pentavalent impurity atom has one electron which is free. So I am marking this way. So this electron is free, and this electron is called free electron. This is what electron? Free electron acquired by one of the impurity atom, one of the impurity atom, pentavalent impurity atom. Okay, so this electron become free. Thus, every impurity atom has one electron free. Pentavalent impurity atom has one electron free, and this electron is the fifth electron. That's why I have written point out here. The fifth valence electron of the impurity atom becomes free, and this electron require a very small amount of energy. So that means, like if I take this impurity atom added with the germanium, then how much energy that is required by this fifth electron? 0.01 electron volt in case of germanium. And if this impurity atom is added with the silicon, then you need how much energy? 0.05 electron volt energy in silicon to leave its atom, and to move to the what state? To the which band? Conduction band. Okay, but usually what happen at room temperature? Let me take this semiconductor at what temperature? Room temperature. Then this fifth free electron, okay, which are free from every impurity atom, can even move from conduction band move to the conduction band even at what temperature? Room temperature. Okay, so just considering that one impurity atom has one free electrons. So just imagine how many impurity atom can add. So many impurity atom can be added in a crystal to make the number of free electrons more. So that means every fifth impurity atom has one free electrons. Then if you add millions of impurity atom, then it have millions of what? Free electrons. Okay, and they can even move from to the which band? Conduction band at what temperature? Room temperature. So what happened under this case? By adding number of impurity atoms to the pure silicon or germanium semiconductor, the number of free electrons increases. We can increase the what? The free electron, number of free electrons. So in this case, what happened? The conductivity of this semiconductor increases. So one of the way that we can increase the conductivity of semiconductor is by adding the impurity atom. But out here we are adding what? The what atom? Pentavalent impurity atom. So as I said already, the advantage of adding pentavalent impurity atoms is to make the number of free electrons, okay, more, okay, to increase number of free electrons in a semiconductor. And this impure semiconductor is also called N-type semiconductor. See, it's called what type? N-type semiconductor. Why it is called N-type semiconductor? Because it has an excess of negative charge as free electrons. Because out here, free electrons will be the charge carrier, mean charge carrier. Okay, and this free electron will be excess. There will be excess of free electrons which can conduct electricity when this semiconductor is connected to the battery or cell. That means in the presence of electric field, the excess of free electrons which are present in this type of semiconductor, okay, can conduct electricity, and electron as a negative charge, okay, which has excess in number, okay, can conduct more electricity. That's why this particular semiconductor is called N-type what conductor? Semiconductor. Under this semiconductor, this impurity atom that you can see, which is actually a pentavalent impurity atom, is also called donor atom. So let me just give the name of this atom as what atom? Donor atom. So this impurity atom, pentavalent impurity atom, which is added in the semiconductor, is called donor atom. So why they are called donor atom? Because they donate the conducting electron to the crystal. Because every impurity atom has one electron free, okay, excess, okay, and that will be donated, okay, to conduct the what? Electricity. That's why this atom is also called donor atom. Now we will discuss in detail about the band structure of n-type semiconductor, also called the energy band diagram of n-type semiconductor. Okay, and this can be understood with the help of this diagram. So this is the energy band diagram of n-type semiconductor. Now if you look at this diagram, the fifth valence electron means this valence electron, okay, of every pentavalent impurity atom which is added to the semiconductor, okay, acquire their own energy level, acquire a what? Own energy, a discrete energy level, and this energy level will be just below the conduction band. So this is valence band, this is conduction band. So that means every free electrons of the impurity atom added to the semiconductor acquire their own energy level, okay, and but this energy level will be just below the conduction band. That's why you can see there is a dotted line which I have drawn. This dotted line is the energy level acquired by this fifth electrons, valence electron of the impurity atoms. And this energy level for germanium is how much? 0.01 electron volt just below the conduction band, and 0.05 electron volt just below the what? Silicon conduction band for silicon. And this energy level is also called donor level. We also call what level? Donor levels. That's why the energy of this donor level is marked by letter ED. So energy of this donor level is called ED. Okay, now why they are called donor level? Because this level of energy are the energy acquired by the free electrons, okay, and these electrons can easily move to the which band? Conduction band. If you connect this semiconductor with a cell or battery, or even if you take this semiconductor at what temperature? Room temperature. Okay, so at room temperature, or if the temperature increases by little amount, then these free electrons which are present in the donor level or in this energy level, okay, acquire this much energy, just this much energy in case of germanium silicon, to move from this level, donor level, to which band? Conduction band. That's why at room temperature, the fifth electrons which are present in this level, okay, donor level, okay, are thermally excited from this donor level into the which band? Conduction band, and they move as a charge carrier. This electron can move as a what carrier? Charge carrier, when you connect that semiconductor with a cell or battery. That means in the presence of what field? Electric field. That's why at room temperature, almost all the electrons in the conduction band, okay, all the electrons you can see in the conduction band are come from the which level? Donor level. That means whatever electron present in the donor level, due to the addition of this pentavalent impurity atom, they can simply move from this level to the which band? Conduction band. They move to the conduction band. That's why you can see in the conduction band there are number of electrons present in the conduction band, and this most of the electrons which are present in the conduction band now is actually due to the electron move from this donor level to this conduction band at what temperature? Room temperature. And only very few electrons can move from valence band to which band? Conduction band. So you can see out of how many electrons out there? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons present in the conduction band. But out of 8 electrons, only 2 electrons are moving from valence band to conduction band, because there are how many holes? 2 holes. These are the hole. These are the hole, and these are the what? Electron. These are the what? Electron. So out of 8 electron, 6 electron have moved from donor level to the conduction band, okay, whereas 2 electrons have moved from valence band to the conduction band. Because when 2 electrons move from valence band to conduction band, how many holes has created? 2 holes. Okay, so you can clearly see in the diagram that majority of the electrons that are present in the which band? Conduction band, and minority of the holes that has created in the which band? Valence band. So look at if you compare the concentration of these electrons and hole present in the conduction band and valence band. So concentration of electrons, free electrons in the conduction band has maximum, whereas the concentration of hole is in the valence band is what? Minimum. That means in case of n-type semiconductor, electrons concentration is more than the hole concentration. That's why if you look at this case as of n-type semiconductor, as I've written already, the concentration of electron, which is marked by Ne, is more than the hole concentration, which is marked by NH. That means Ne is much greater than NH, but Ne is nearly equals to Nd, capital Nd. Now, what is capital Nd? Means concentration of donor atom, donor level. So, donor level concentration means the concentration of the electron present in the donor level, which almost nearly equals to the concentration of electrons present in the conduction band. This means this majority of the electrons, as I said, in the present in the conduction band, that means the concentration of free electrons in the conduction band is mostly due to the what? The which level? Donor level. Whereas concentration of hole is very less in the which band? Conduction valence band. So under this condition, if this semiconductor, N-type semiconductor, is connected to a cell or battery, then what happen? Electrons, okay, which are present in the conduction band can move, and hole also can move. That means the charge carrier are electrons and hole. See, both are the charge carrier in N-type semiconductor, but the majority charge carrier in N-type semiconductor is what? Electrons, and minority charge carrier in N-type semiconductor is what? Holes. So electron as a negative charge carrier are the majority charge carrier which conduct more current, okay, conduct current or conduct electricity when this semiconductor is connected to a cell or battery. That's why that is the reason that this semiconductor is also called N-type semiconductor. Therefore, in N-type semiconductor, I have already said that electrons are the majority charge carrier and holes are the minority charge carrier. Both are charge carrier, but one is called as majority, another is called as minority. Means more current conduction takes place more due to the movement of electrons than the what? Holes. So this is a detailed explanation of N-type semiconductor. Now in the similar manner we do another type of extrinsic semiconductor, that is called P-type semiconductor, and that you learn in the next YouTube video.